Dear students, I welcome you for the topic related to the mixing operations in the subject of chemical equipment design. So, the mixing operation is one of the important aspects in our chemical process industries. The term mixing is applied to the operation which tends to reduce the non-uniformities in composition, properties, temperature of the material. So what it means actually, the mixing is to reduce the non-uniformities. That is the basic purpose of mixing, to reduce the non-uniformities in the different respects, that is of composition, properties, temperature. These are to be made uniform throughout the mixture in a vessel. So this mixing operation is the heart of your chemical process industries. So mixing system can be your solid, solid liquid, solid and gas. Then it can be your liquid, gas liquid, or it can be your gas and gas, or it can be combination of different phases, that is gas, liquid and solid phases. So the different phases, they are incorporated in the process of mixing with the purpose to reduce the non-uniformities, to make them homogeneous, to make them consistent, is the basic purpose of mixing. Then we add the terminology of agitation to that. Now there is a difference between the mixing and agitation. Mixing is a process, agitation is a means, agitator is a means. A agitator that is used to mix the different phases. So agitation is a process. As a result, you get a good uniform mixture. So that is the basic difference between the agitation and the mixing. Agitation, you require an agitator, and in the process of mixing, once you agitate, you get a mixture. So agitation is a mean whereby mixing of phases can be accomplished, and by which mass and heat transfer can be enhanced between the phases or with certain external surfaces. In its most general sense, the process of mixing is concerned with all combinations of phases, of which the most frequently occurring ones are. That is, the gases and gases, they can be mixed. Gases, when they are mixed into the liquid, that process is called a dispersion. That process is called a dispersion. Then the gases with solids, it's a process of fluidization. You make the solids to move in a fluid like motion with the energy supplied with the gases. Then it is also associated with the pneumatic conveying and drying of the solids. Then the phases, that is liquid into the gas, that is spraying and atomization. When gas, that is dispersed into the liquid, and liquid into the gases, that is spraying or atomization. The different processes are there, like spray painting. In the spray painting, you spray the liquid into the atmosphere. So it's a liquid into gases, and when it's a gases into the liquid, that is, you are dispersing the gases or gas bubbles into the liquid, that is a dispersion. Then fifth one, liquid with the liquid, you can form an emulsion, you can do the dispersion, blending. Then liquids with granular solid, it can be the suspension or dissolution. If it's a immiscible solid and liquid, it will form a suspension. And if the solids, they will be soluble into the liquid, it is a dissolution. Then paste with each other and with the solids, that is related to the liquid, pseudo homogeneous liquid that is formed. Then solids with solids, it's a mixing of powder, or it can be the blending of polymers, you can say. So these are the different operations which require the processes. Then when mixing is used, it is used to make uniformity in composition, temperature, properties of the material. Mixing operation improves the properties of the material, and mixing gives the desired flow pattern to give the materials. Desired flow pattern that is also obtained. So one by one we'll understand these different operations associated with the mixing processes: suspension, dispersion, dissolution, heat transfer, blending, chemical reaction, crystallization. All these require the process of mixing. So a good mixing system should have the following characteristics. First is the minimum power requirement. Whatever the process of mixing or how much efficient that mixing operation should be, that will basically depends on your minimum power requirement. That means it should be best economically possible. And when you talk efficient mixing in the optimum time, that means with the minimum time or the desired time, you should get the uniform composition throughout. Efficient mixing means the uniform composition is expected throughout the mixture. Everywhere the concentration will be the same. That means the efficient mixing. The minimum maintenance of all your mechanical parts, then its durability and trouble-free operation. Then the unit should be the compact one. So these are the basic requirements for the good mixing. Out of that, this minimum power requirement that is talked everywhere. The rest of the things, that is economy, maintenance, they're more or less fixed cost. Minimum power requirement is more focused towards the running cost. And these mixing operations, the power required is the most important thing that is to be considered for calculation. Then first process is the solid suspension. Now it's a physical mixing operation basically, and this involves the liquid and solids, but the solids, they are immiscible in the liquid. That means suspending of fine solid particles in a liquid, that is in the catalytic hydrogenation of liquid, solid catalyst particles in the hydrogen bubbles are dispersed in the liquid. So this hydrogenation process, it incorporates the gas, that is the hydrogen bubbles, solid catalyst particles, nickel, and they are dispersed in the oil. So that is what the hydrogenation processes that is taking place. Second example, a slurry of uniform composition having the particles in suspended form is to be prepared. Now you will perform one of the experiments of a sedimentation in your solid fluid operation. There you take a calcium carbonate solution. That means the calcium carbonate is dispersed, suspended into the water. That means first you will stir it with the help of a glass rod to get a uniform slurry to form a suspension. When you disperse, when you distribute, when you stir with the help of a glass rod, this calcium carbonate will be uniformly distributed into the water to form a slurry. That is nothing but a suspension that is formed. And if you will allow it to keep it for certain time, then it will get settled. The process that will be the sedimentation process. Paint is also one of the best examples of solid suspension. Here the energy requirement that is of our main focus is depends on the percentage of solid in suspension. How much percentage of solids that is to be suspended. Then the particle size, particle velocity and the density, wetting characteristics of the solid, how the solid and that liquid they will be adhered to each other, their wetting characteristics. Then quality of suspension, whether it should be a uniform suspension or just a motion of particles that is desired. Then second, it's a process of dispersion. The dispersing a gas in a liquid as the fine bubbles. So it can be a gas liquid. It can be a liquid process also. That means two immiscible liquids. Then it can be the solid and liquid like your toothpaste, pigmented paste. That is the pseudo homogeneous mass that will be formed. The dispersing a gas in a liquid as the fine bubbles, such as the oxygen from air in suspension of microorganisms for fermentation or for the activated sludge process in the wastewater treatment. The energy requirement per unit volume can vary widely. Then the information required for producing the dispersion is as follows. The type of a dispersion, that is the liquid dispersion, solid liquid, gas liquid dispersions can be there. Then the quantities of the each phase required, the time allowed for producing the final dispersion of product, then the fineness of dispersion required to produce by the mixer. That is what the hydrogenation of oil is the important example for this gas liquid dispersion, or the air bubbles that is passed into the water where the microorganisms are available either for fermentation or for the wastewater treatment. Then if you increase the gas rate, the energy requirement for obtaining the uniform dispersion that also increases. If the gas rate increases, the energy requirement to obtain the uniform gas dispersion increases. Similarly, if the temperature increases, the rate of reaction between the gas and liquid increases, and hence the energy requirement also increases. The energy requirement for dispersion is function of bubble size, which in turn gives the desired mass transfer rate. If pressure increases, then energy requirement decreases. For pressure, it is inversely proportional. Energy requirement is inversely proportional. This is what a common hydrogenation, oil hydrogenation figure. Then the process parameters, they are also of concern. The details of vessel dimensions, the reaction rate data, volume being handled in the vessel, then operating pressure and temperatures, then gas volume bubbled per unit time, that is the meter cube per second, then time allowed for the final dispersion product, that is the in this amount of the time the final dispersion that is expected. The energy requirement, general energy requirement for vegetable oil hydrogenation, that is around 3 kilowatt per 5 meter cube, and for organic halogenation it is 15 kilowatt per 5 meter cube of volume. Then there is a process of dissolution. This is associated with a miscible solid into the liquid. That means the solid particles plus liquid, the solid particles will get dissolved and you will get a solution. Solids are dissolved in liquid to produce this solution. Hence, the good circulation is to be provided around the solid particle. Now, where the role of this agitation or mass transfer that is coming into the picture from the point of view of chemical engineering is this. The good circulation is to be provided around solid particle. That means this solid particle that should exposed, if this solid particle that should be continuously exposed to the liquid, fresh liquid, it has to be continuously exposed to the fresh liquid. This good circulation is to be provided around solid particle. So that means the fresh liquid and the solid surface, they will come in close contact. That is why we are trying to move the liquid in this process, so that the good contact interfacial area that will be good. In some dissolution processes, for example synthetic rubber, solid resin, the viscosity of solution progressively increases. Hence, the final solution becomes highly viscous with very high solid contents. So, for example, the sodium chloride solution in the 10 meter cube tank may require 3 kilowatt of energy, the energy requirement. However, 1% of carboxymethyl cellulose, that is the CMC, in 10 meter cube tank may require 10 to 15 kilowatts of energy. That means it depends on the solid. CMC, it forms a viscous solution, and that is why you require a much higher energy as compared to the sodium chloride. Then the information for producing the dissolution, the percentage of solid in suspension, then the physical characteristics of gas and liquid at initial stage and final product, then solubility of particle in liquid and its temperature, then allowable dispersion time. First it has to be dispersed, then it will dissolve. Solid particles, when the dissolution that is associated, first it is the dispersion that is taking place and then the dissolution that is taking place. Then the process of crystallization. In the process of crystallization, agitation mixing system selection is done according to the heat transfer application, necessitating the good flow of solution past the heat transfer surfaces. You must have performed certain experiment in your inorganic lab so that you get a certain crystals. In that, you stir the solution and allow the certain nuclei or crystals to develop. You go on continuing the stirring it so that you will get the good quality crystals. So to get a good quality crystals, one has to take the important consideration of agitation. Then and only then you will get the good quality of crystals. A certain flow direction that is required to get the good crystals. Then it is also required the heat transfer surfaces. The rate of heat transfer depends on the mixing pattern. The rate of surface renewal at the heat transfer surfaces, then agitation of the fluid to increase the heat transfer between the solid and a coil or jacket in the vessel wall. So the process of agitation, it increases the heat transfer. The turbulence that is created because of agitation, the turbulence, the motion is given to the fluid particle. As the motion is given to the fluid particles start moving. Once they move, that means every time they come in contact with a fresh liquid, and that increases the heat transfer. Then the process of blending of miscible liquids. Again, it's a simple physical mixing operation without any chemical reaction. Blending doesn't involve the chemical reaction. Blending of two miscible liquids such as the ethyl alcohol and water. Then the changes in the, or it can be the kerosene is blended in the petrol, or kerosene is blended in the diesel. Then sometimes it's a fresh polymer that is blended with a recyclable polymer. Then glycerin is blended in water. The change in the physical properties that is observed, the composition of blend needed and the time allowed to obtain the final blend has considerable effect on energy requirement. The time required for one turnover depends on whether the components are readily miscible or they have the wide different properties. Then again, the chemical reaction, this is the most important part associated with our chemical industries. The rate of chemical reaction is influenced by mixing in the vessel. How the different phases they come in contact with each other so that the higher rates of chemical reaction you will be getting, and you will get the desired product with the minimum time. Rate factor, that is very important for our chemical reactions. The consideration of agitation are same as in blending, dispersion and dissolution processes. So these are the different operations we have talked about. But these mixing operations can be carried out in different ways. For example, in a vertical tank mixer, then side entering mixer, horizontal mixers, planetary mixers. These are the different processes. Now, in addition to that, the different kinds of mixing processes that is existing. Then mechanical mixers. This is the concrete is mixed. Concrete is produced from your sand, gravels, and cement and water. So there you are rotating the whole tank, rotating the tank. That is a mixer, like concrete mixer. Then there are certain static mixers. So static means the mixer itself is a stationary. So in a pipe that is fitted with the certain internal baffles, like your helical structure. When the helical structure that is available inside a pipe, then the flow will get a certain direction, rotary direction, and in that rotary direction the process of mixing that is taking place. So these static mixers, they are pipe mixers. So the mechanical mixer, then static mixer, rotating tank mixer, then agitator mixers. This is of our concern. Agitators working with the pump, then agitator turning tank to gas. So looking at these figures, A, that is a mechanical mixing using the turbines. Then mechanical mixing using the bladed impellers that is used. That means we are using the agitator in this case, as well as this is the agitator that is used. Then the hydraulic mixing, that is the another way by which you can do the mixing. Hydraulic mixing, that means you are taking out the fluid and again pumping that fluid back into the tank. That is what the hydraulic mixing. Again here also the hydraulic mixing that is taking place. That means a pipe that is there, and through another pipe or through a capillary you are injecting a dye. So there is a flow that is available and you are injecting a dye. After certain distance you will get a uniform homogeneous color zone. That is what a Reynolds experiment is. So this is also a hydraulic mixing, but in general case the hydraulic mixing, a pump that is used and the same fluid that is incorporated in a tank. Then the D, the pneumatic mixing. Then E, that is the pneumatic mixing with automatic regulations. This is in case of a pneumatic liquid and the air that is incorporated. And this is the hydraulic mixing with anti-foaming shower. That means to avoid the foam, you are spraying the liquid back into the vessel. Whatever the liquid that is collected into the vessel, again that is sent back so that the foam reduction will be done. So these are the different ways by which you can do the mixing. Your mechanical mixing, hydraulic mixing, pneumatic mixing, and the pipeline mixing. So these are the different methods of mixing the fluids. Now, what basically the agitator system consists of? The agitators are the machines used in industries for mixing liquids together. The purpose of agitators is mixing. purpose of the agitator is to mix, and this promotes the reaction of chemical substances. Why we are doing it? To promote the reaction of chemical substances, keeping the homogeneous liquid bulk during the storage, increase the heat transfer. Then in another words, agitation refers to forcing a fluid by mechanical means. This mechanical means is nothing but a agitator. Mechanical means can be the rotation of a tank itself. Mechanical means that can be the pumping of a fluid. Mechanical means that can be by compressing the air. Mechanical means that is by compressing the air and conveying the solids. Here the compressing the air and passing it through the liquid, or in case of a fluidization it can be passing through the solids. So these are the different ways by which the mechanical mixing, when the mechanical mixing is with the help of agitators, mechanical mixing with the help of an agitator, it is called the process of agitation. Mixing is a wide terminology. The process of mixing that is achieved with the help of different techniques: rotating tank, agitator, then compressors or pumps, and out of that one is your agitator. So agitation, it's a action, putting into the motion by shaking or stirring, often to achieve the mixing, bring stirring or disturbance of a liquid. The techniques mostly involve the agitation by stirring. Means agitators generally they are stirred. The agitation given a rotary action. Agitators they are given the rotary action so that the fluid that will be stirred, the turbulence that will be created into the liquid phase. The agitation is achieved by generating the movement of the fluid liquid phase, and there the impeller that is coming into the picture. So this is due on the mechanical agitator to the rotation of the impeller. So the agitation, this is due to the mechanical agitators due to the rotation of an impeller. The bulk can be composed of different substances, and the aim of the operation is to blend it or to improve the efficiency of a reaction by a better contact between reactive product, or the bulk is already blended and the aim of agitation is to increase the heat transfer or to maintain the particles in suspension to avoid any deposits. In the mixing, it is a superficial, but in agitation it goes to the micro level also. Mixing doesn't help for proper and uniform chemical reaction. The agitation of liquid is made by one or the several agitation impellers. Depending on its shape, the impellers can generate the moving of the liquid, which is characterized by its velocity and direction. The turbulence, which is an erratic variation in the space and time of local fluid velocity. The turbulence, the chaotic condition that is generated, the erratic behavior of the fluid that is observed. Then shearing gives by the velocity gradient between the two layers of the fluid. These two phenomena provide the energy consumption Now there are mechanical features of the agitators. Look at this figure first. Now this is an agitator, a tank that is available. In this tank, a agitator that is provided. Now a tank is nothing but our pressure vessel. So to this pressure vessel, cylindrical shell, top head, bottom head, certain valves, inlet outlets they are provided, and one of the important things required for the stirring, that is your agitator. Now this is the agitator assembly that you can see. Basically it's a shaft and a impeller they are of concern. Shaft and a impeller means impeller which rotates, and when it rotates it also gives the direction to the fluid in the vessel. Once the fluid has got a direction inside the vessel, that fluid will start also moving. Once the fluid that is moved, it will have a certain rotary action, and the different velocities at different layers that will be available. So velocity gradient inside the vessel that is also observed, and because of that the turbulence that is created, mixing that is taking place. Now in addition to this impeller or impeller blades, shaft, there is a mechanical seal that is also available. This mechanical seal that can be the gas glands, and this is to prevent the liquid vapors which is going out from the vessel. Then there can be the speed reduction or speed increase gearboxes. Then there can be the certain coupling between the drive motor and the gearbox. This gearbox that is connected to the shaft, and to prevent the vapors going out from the vessel, the sealing arrangement, either it can be a mechanical seal or the gland that can be used. Then this speed reduction to require or to achieve the desired speed. Motor has a fixed RPM of say 1500 or 3000 RPM. However, this shaft will have or will require a different RPM depending on the attached impeller. For propeller you can have a higher speed, for a paddle you can have a lower speed. So for that purpose you require a gearbox to give the desired speed. So an agitator is composed of a drive device, that is primarily it's a motor, then gear reducer, then sometimes it can be the belts, coupling or transmission, a guiding system of the shaft, then the seal, mechanical seal, then support and mountings on which the motor that is put, or motor that is to be supported. So certain supports or platforms, they are fabricated or welded on the vessel to mount the motor to hold the shaft at proper position. Then the shaft and the impeller. If the operating conditions are under the high pressure or high temperature, the agitator must be equipped with sealing system to prevent the leakages, vapor leakages, to keep the tightened the inside of the tank when the shaft is crossing it. If the shaft is long, it can be guided by the bearing location in the bottom of the tank also sometimes. The various parameters of basic equipment useful for agitation system design. For agitator system design, one has to consider the different parameters. The ratio of liquid depth to the vessel diameter. It can be between 0.5 to 1.5. Generally, it is the 1. Liquid depth to the vessel diameter. L by D ratio, length to diameter ratio. Then liquid depth. It indicates the cylindrical height in the case of a flat bottom vessel. If the vessel has dish bottom, then the distance up to the center of the dish is considered as the liquid depth. If the coils are provided in the vessel for heating or cooling purposes, then their pitch should not be the close one. If the baffles are for the better mixing and to promote the turbulence, this should be welded to the vessel wall in case of a low viscosity vessel liquids, and in some clearance should be maintained within the vessel wall in case of a high viscosity liquids. That means when the baffles we are providing, if this is the vessel and these are the baffles, if it is a low viscous liquid, no necessary of providing the clearance. But if it's a viscous liquid, then there is a necessity of providing the clearance between the pressure vessel shell and the baffle, so that the viscous liquid should move from this gap. The baffles are for better mixing and to promote the turbulence. This should be welded to the vessel wall in case of a low viscosity liquid, and some clearance should be maintained within the vessel wall in case of a high viscosity liquids. Other fittings in a vessel are your dip pipes, thermowells, draft tubes should be fitted at proper location so that they do not disturb the flow pattern generated by the agitator in the vessel. Now this flow pattern, they are also very important. You get the desired rate of a reaction. This generated flow pattern plays a very important role. Besides that, the other important considerations in designing are the determination of amount of energy required or the power required for satisfactory performance of mixing operation. The processes has to be well defined. For example, mixing system is to be designed to make up and hold in uniform suspension. For example, I want to make a 15% slurry of calcium carbonate and hold it for the 3 hours, or I want to make a slurry of terphthalic acid into the ethylene glycol and to make a slurry and hold it for say 2 hours in slurry mixing tank. It's a continuous process, but even though the certain residence time that is to be given in many cases, then the description of the component to be mixed, their properties at initial and final stages, overall specific gravity, initial and final viscosity, concentration, etc. They determine your power requirement. Then details of the tank geometry. Tank geometry is very essential to understand. To give you the flow pattern, desired flow pattern, they are obtained in the similar tank geometries. If the tank geometry changes, the dimensions of the tank changes, then may not be necessary that you will get the same flow pattern and you will get the desired reaction rates and desired products. They can vary. There are many processes which in a lab scale you get a certain product. However, when they are enlarged to the industrial scale, they may not give the desired products. There, these flow patterns, they are of very much importance. So this is what is related